Hello and welcome back to part 2 of the Delaware Tech Physics 111 Exam 2 Prep and Practice Exam covering forces and energy. In this section, we're going to talk about Newton's 3 laws of motion. So Newton's first law of motion is also called the law of inertia. Inertia is the resistance to changes in motion, really because the object has mass, and its resistance is unless an external force acts on it. So what does that mean? That means if the object was standing still, if it was at rest, it'll stay at rest unless there's a force acting on it. And if it's already moving in a constant speed in a straight line, in other words, it has a constant velocity, it also will keep doing that unless an external force acts on it. So mathematically, what that means is if the net force is zero, in other words, we're not putting an external force on the object, the acceleration is zero, meaning if it was stopped, it'll stay stopped. If it had a velocity, it'll keep that velocity. The velocity is constant. And the second law of motion is also called the law of acceleration, and this relates net force, acceleration, and mass together in one formula. And what it says is when a net force acts on an object, the object will accelerate. In other words, when net force acts on a mass, it will achieve an acceleration. And that acceleration is described in these two versions of the same formula. I'll say the second one first. Net force equals mass times acceleration. But it's more useful in the first form, especially when we're interested in how much acceleration happens. Acceleration equals the net force divided by mass. For instance, when you're doing your free body diagrams, you work out what the total net force is, you divide it by the mass, and that tells you the acceleration. And the acceleration and the net force are always, always, always in the same direction. If there's no net force, there's no acceleration. But the formula also tells us that that acceleration is directly proportional to net force, meaning more net force, more acceleration. Less net force, less acceleration. I double one, I'll double the other. But the formula also tells us that acceleration is inversely proportional to mass, meaning if I increase mass, I will decrease acceleration. If I decrease mass, I will increase acceleration. And the easy way to think about that is just using the bowling ball and ping pong ball analogy. If you use the same force on two completely different masses, they will have two completely different accelerations. And if you're trying to remember which way it goes, just think about kicking a bowling ball with a certain amount of force. It's going to have a small acceleration. Kicking a ping pong ball with the same force will have a huge acceleration. And that's Newton's second law. And Newton's third law is the law of action and reaction, which tells us that whenever two things interact, it doesn't matter whether one is alive and one is not alive. If two things contact each other and there's any force between them, both of them are exerting the exact same force on each other, just in the opposite direction. So mathematically, we would say the force of A acting on B is exactly equal in magnitude to the force of B acting on A, just in the opposite direction. So we use a negative sign to represent that. All right. So what are the implications? Well, the implications from this, especially with Newton's third law, is if you're at rest or you're at constant velocity, in other words, your velocity is either constantly zero or it's constantly something, then that means there's no change in the velocity. That's what constant means. No change in velocity, well, then you can't have a change in velocity over time, so therefore there's no acceleration. That's the definition of acceleration. And Newton's second law tells us that the net force is equal to the mass times acceleration. So if you have no acceleration, you can't have any net force, and vice versa. If you have no net force, you can't have any acceleration. And we just call that situation equilibrium. So if you have any one of these being true, you have all of them being true. If you have any one of them being false, none of them are true. So If they're if they were false, if any one of these was false, that means there is an acceleration and that there is a net force. In other words, the sum of the forces is not zero. They don't cancel out. They're not balanced. Okay, so now let's use our knowledge of Newton's three laws of motion, look at a few examples, and determine which law explains this statement and why. So the first statement is, if you kick a tennis ball and a basketball with the same force, the tennis ball will accelerate more. Well, this sounds just like the example I gave you with the bowling ball and the ping pong ball. You apply the same force to two different masses, you're going to get two different accelerations. And the basketball has more mass than the tennis ball. The one with less mass, the tennis ball, will accelerate more if you use the same force on it. If you kick a tennis ball and you kick a basketball with the same force, the tennis ball will accelerate more. And this is a version of Newton's second law. So we'll fill in 2 for the number of the law. There. We'll put it in red so you can see it. And the explanation is Newton's second law. Let's get that in red so it's nice and visible. Newton's second law tells us that when net force is constant, mass and acceleration are inversely proportional. Now, you don't need to know inversely proportional, but you do need to know what it means. This means that when mass goes up, acceleration goes down, and when mass goes down, acceleration goes up. They are inversely related. One goes up, one goes down. And that's because of the formula itself saying acceleration is equal to the net force divided by the mass. And it's easier to see when you see it written properly with the net force on top of the mass in a fraction. But you can see because the mass is in the denominator and the acceleration is in the numerator. I know it doesn't look like a fraction, but it's a over the number 1. When they're on opposite sides and of the equation and opposite sides of the fraction, they're inversely related. One goes up, one goes down. Okay, let's look at the next one. We have a hockey puck on smooth ice. All right, why are we saying smooth ice? Smooth ice tells us that there's no significant frictional force that might slow down the hockey puck on the ice. And it says that the hockey puck on this smooth, frictionless ice will keep moving across the ice at a constant velocity. Well, if nothing's going to change it, if there's no added net force to the hockey puck, and we're assuming there are no forces, no horizontal forces on the hockey puck, it has two vertical forces. There's the weight force and the normal force, but those balance each other out. And horizontal forces, there are no horizontal forces, so if it's already moving at a constant velocity, it will keep moving, and Newton's first law tells us that. So Newton's first law tells us that an object in motion, meaning constant velocity, will stay in motion unless acted upon by an external, in other words, something new, net force. Well, there is no net force, so the hockey puck will just keep going until the ice runs out. Now let's look at the third example. A rocket pushes escaping gas backward, and the escaping gas pushes the rocket forward. Well, the rocket is pushing the gas backward. The gas is pushing the rocket forward. Well, this is a perfect example of Newton's third law. Newton's third law says if some object A is acting on some object B in one direction, then object B is acting on object A in the exact opposite direction. So Newton's third law, red, Newton's third law tells us that for every action, there is an opposite, meaning opposite direction, and equal, meaning equal magnitude, equal size, reaction. And in this case, the rocket acts on the gas, and the gas acts on the rocket. They act with exactly the same amount of force, but in exactly the opposite direction. And I want you to notice something about this example. This is the reason why rockets work even in deep space where there is no air. People think, oh, the rockets or jets work because they're pushing out some kind of burnt fuel or gas out the back of the rocket, and it's pushing the air, and that's what's pushing the rocket forward. No, they don't need air to do that. It's just the rocket acts on the gas as it's releasing the gas, and the gas acts on a rocket. And in fact, this is a very similar situation to what happens when you blow up a balloon, you fill it with air, but you don't seal off the balloon, and then you just let the balloon go. What happens? The balloon flies away. That's because the balloon is pushing the air out of the back of the balloon, and the air is pushing the balloon forward. And that's why the balloon just flies around the room. Okay, now let's look at the last example. And the last example is a special example because there are two correct answers. We have a situation that says a bowling ball is rolled into a tennis ball. In other words, the two hit each other. The force that the tennis ball exerts on the bowling ball is exactly equal in magnitude to the force that the bowling ball exerts on the tennis ball. So the two interact, and the bowling ball creates the same force on the tennis ball that the tennis ball creates on the bowling ball. Of course, they're in opposite directions. Well, that's a perfect example of Newton's third law. So let's just write that in here. Newton's third law tells us that if the bowling ball strikes the tennis ball with force, the tennis ball will exert the exact same amount of force on the bowling ball. Just in opposite directions. Now, if we look at the rest of the question, it says the tennis ball, however, accelerates much more than the bowling ball. But we just said that they have the same force on each one. The force on the tennis ball is the same as the force on the bowling ball. Why is the tennis ball accelerating more? Well, it's accelerating more because it has less mass to accelerate. The same amount of force on a smaller mass, that's Newton's second law. And we'll just put it up here. It says second. Newton's second law tells us that for the same force, the smaller mass will have a larger acceleration. The larger mass will have a smaller acceleration. And the same situation will be true if you have a gun shooting a bullet. The gun is much more massive than the bullet, but when the gun shoots the bullet, the force that the gun has on the bullet is the same that the bullet has on the gun. Except the bullet has much less mass, so it will accelerate much more. The gun will still accelerate. That's the kickback in a gun. Another example would be you standing on the earth. The force of gravity on you, your weight, is the earth pulling on you. It's the force of the earth on you. But you have the exact same force on the earth. Those two forces are identical. It doesn't seem that way, but they are. But you have much, much, much less mass than the earth. So you accelerate downward with the acceleration of little g, while the earth barely accelerates at all. We can't possibly measure such a tiny acceleration upward of the earth. So you only think about it in one way. The reason why you don't keep accelerating towards the center of the earth is because there are other forces on you, like the normal force, which is the ground pushing back up on you, preventing you from penetrating the earth. All right, let's stop here. And when we come back, we'll begin looking at steps for solving free body diagrams.